Thank you very much. I want to start thanking Veronica, Jan, and Ted for organizing this wonderful meeting and for inviting me, and the Institute of Mathematical Science for hosting it. Really helps me, these kind of meetings, with a lot of time for discussion and lots of interesting people to talk to. So I really appreciate this opportunity. So today I will talk about normality, normality for distributions different from the uniform, and a bit about a finite state dimension. It is a bit scary to be talking about this after Jacques Lutz, but please don't compare. Let's see. This is joint work with Xian Huang, Don Stuhl, and Jacques Lutz. Normality is a very robust notion, we all know. And for instance, I have listed a few of the equivalent characterizations that we are familiar with. Let's see if I can look at it. Okay. So these are like the basic characterizations of a normal sequence. The block frequency should be the expected one, 2 to the minus length of W, for blocks of length W. And then it doesn't matter whether it's overlapping or non-overlapping. That's still the same. Or we have, excuse me if there are any mistakes here. I realize I said equidistributed, I mean uniform modulo 1. So we have characterizations related to these sequences viewed as real numbers and their equidistribution in the unit interval. Then in computer science, challenging Jacques' borders of the world, we are interested very much in very low resources, computing devices such as finite state machines. So for instance, I am aware that people in cryptography, they view our normal sequences as like useful random sequences. So we know that we can characterize normality using finite state gamblers. And there are two characterizations. First, we know that normality coincides with sequences on which there's no possible success for a finite state gambler. Equivalently, no finite state gambler succeeds exponentially, infinitely often. So this is mostly what I will be talking about today, about these two equivalent characterizations. And then there are more, but actually Jack did backwards. I thought he would be covering a lot about gamblers and not much about compression, but then he did it the other way around, so we have heard a bit about this. So actually, but let me just point out that the equivalent characterization for compression is also double. So no finite state information lossless, finite state, sorry, I forgot. Oh yeah, finite state is there. Finite state information lossless compressor compresses infinitely many prefixes of S. Or the other way, actually you could also say compresses the compression ratio is 1 somehow. So you also, in this compression characterization, you also have like the same kind of double property that I have outlined before, that the compression ratio, sorry, it goes to 1, and also, did that right? Sorry, this is not, okay. And this is also maximal in that sense. And they are both equivalent. So the fact that you cannot, that your compression ratio goes to 1, and the fact that you're almost at maximal length. And well, there's also an alternative characterization. using more information content. I will not mention it today. Jack hasn't mentioned it that much, but somehow the idea is that you don't need to use information lossless compressors to do some sort of Kolmogorov complexity characterization. With finite state transducers, you can still do it in a more Kolmogorov complexity way. Okay, and there are a few more interesting ones. Apologies if your favorite characterization of normality is not there. Let's do it with a different probability distribution. So just take a probability measure on the alphabet, okay? And actually I forgot, but let's say it's a positive probability measure. There are no zeros. And then you can still have a very reasonable notion of normality. So for instance, you can still look at the frequency of each block, W, on a certain sequence. And if the frequency is the right one, you call it alpha normal. Which is the right one? Well, the alpha of W. Okay, so this is defined for the alphabet. You just multiply the probabilities of the different symbols. So it happens for yes, overlapping blocks and for non-overlapping blocks. So you still get the same concepts, and this is what more or less Borel calls alpha normality. You can also have this property on the real numbers represented by this sequence related to equidistribution. And you can have a gambling characterization of normality. And this is what I will be covering today. I'll try to define gamblers a little bit. So alpha success is related to somehow the betting of the finite state machine in connection with the underlying probability distribution alpha. And so you have both cases. So you know that you cannot succeed infinitely often, and actually you cannot succeed exponentially infinitely often. Those are equivalent. And you can also do it using compressors. And I will not talk much about this, but let's say that for compression, since you have an underlying distribution alpha, what you're going to be looking at is the self-information content of a prefix S0. So this is a prefix of the first n symbols of sequence S. That is the one you're defining to be normal. So this is the quantity that will substitute the length here. So somehow you're going to be looking at this information ratio. So instead of the length, you're going to have here this. Okay. So this is related to the, given that the alpha is the underlying probability distribution. Okay, so if you look at the compression ideas, the sequences that have a higher alpha probability, you're going to find them more often, so you want to compress them more, and self-information is related to that. I will not get into that more today. So what I will be talking today is a precise quantification of these two characterizations of normality. It's the characterizations that have to do with gambling, so they have to do with no success or no exponential success. And the reason why these two characterizations are equivalent, as Jack Lutz mentioned, is related to a theorem by Schnorr and Stim from the 70s, in which they distinguish the kind of success that you can find on normal sequences and the kind of success that you can find in non-normal sequences, in fact, can or cannot. So today I will quantify exactly Schnorr-Stim theorem. And in this quantification, it turns out to appear a very interesting quantity, which is a divergence between probability distributions. So somehow measuring how different two probability distributions are. And on the way, there will be another characterization of normality using this concept of divergence of probability distributions. And it will be the divergence between the underlying distribution alpha and the empirical block distribution that is created by the sequence S. Okay, so you just do the accounting, the frequency, and this gives you a distribution. Of course, depending on the length of the prefix of S you take, you get a different one, but this somehow goes to a certain limit, or you want to look how this evolves. This is what we will compare with the underlying distribution alpha. Okay, maybe a bit more relating finite state dimension, but I usually speak too slow, so let's see. So this is the theorem I will be mostly talking today. So Schnorr and Stim prove in 72 that if a sequence S is not normal, then there is a finite state gambler. I will try to define this later, but some sort of gambler that is only using finite state device that wins money at infinitely often exponential rate, betting on S. So for non-normal sequences, you have exponential win. Whereas for normal sequences, any finite state gambler fails, I can't say the word in English, fails very much. In fact, it loses money at an exponential rate. So this is a very wide dichotomy, and this is, I'm going to quantify exactly how much money you win when you are not normal and how much money you lose if you're normal. Okay, so this is more or less the result. There are several things here that I haven't defined yet. Let me try to give you an intuition. This is not exactly the theorem, but close. So if you are not normal, the infinitely often exponential rate of winning is true to the divergence, this I will define before, between the empirical distribution caused by S and the underlying distribution alpha times the length of W. Whereas if you're normal, the exponential rate of loss is related to the risk that the gambler takes. I will talk about this later too. Okay, so let me give you the definitions from information theory, mostly entropy and divergence. Please stop me if this is too fast or the other way around. Just tell me, go. So this is Shannon Entropy. Assume that you have just a probability distribution on the alphabet, for instance, on an infinite set. And the Shannon Entropy is this sum here. This log of 1 over pi of A is the self-information of A. So somehow it relates of, depending on the probability of symbol A, you're going to use more or less symbols to codify it, okay? So this is this log, which is always kind of the base 2 log, is related to how many symbols you would use to code A according to pi. And you take the expectation. So this is the entropy. This is probably something you have seen before, so I will not. So this is a nice curve. If you only have 2 symbols, so this could show you how the entropy evolves. And this is the set of probability distributions with 3 symbols. And I wanted to show you these nice pictures for a reason. They have been done by my co-author, Xiang Huang. And well, you can see that the entropy looks very rounded, very well-behaving curve. Let me move to the second definition related to information theory today, which is the Kullback-Leibler divergence. Okay, this one, you have 2 distributions, and you want to quantify how different they are. Okay, so this is, the definition is, you're going to do the expectation, the pi expectation of the logarithm of pi over rho. Okay? So note well, you may have seen this definition before, but in case you haven't, know that you can, of course, separate this into two sums, one with pi and the other one with rho. And what you have here is the entropy of pi. Okay? And so what are you doing? Well, rho can be viewed as a subjective probability, and pi is the real probability. This is why I am taking the average related to pi, because pi is the real word. So this is what we will do later when looking at normality. For us, the pi is going to be related to the empirical distribution of the sequence. So what D quantifies is like the difference between the average code length of the coding scheme rho, and an optimal coding. Okay, so this would be more or less the way rho tells you to code like this, and this is the optimal one, and you try to compare them. Okay, this is an information theory way of interpreting this. Notice that then this distance, this divergence, is going to be always positive, and the upper limit is going to be related to the minimum value of rho. Okay, so well, this is easy because pi is bounded by 1 and you just bound everything, but this upper limit is reachable. Let me show you only a couple of pictures of how this goes. For instance, for rho being the uniform distribution on 3 symbols, you can see how this D evolves for different pi. As I tell you, these pictures have been done by Xiang. I just wanted to show you how nice and how continuous this D function looks. This is for other case. I will not try to comment on these pictures, but more, I want to just have the feeling that all this is really nice. Actually, what happens with this divergence is that if you have, if you have to, cannot remember. If this goes to 0, okay, then this is equivalent to the divergence going to 0. Actually, usually the other way around. It doesn't really matter. It is not symmetric, but okay. So this is really useful. Okay, so it's not a distance divergence, but it behaves very well in the sense that whenever your two distributions are the same, the divergence is 0, and that's the only case. So, okay, well, I should have written, I didn't write it very correctly, but this is, if these two approach each other, then the divergence approaches 0. Okay? I'm sorry. Okay, never mind. So let's go faster. I just wanted to show you a bit of how this divergence shows up in the quantification of a steam Schnorr's theorem and in the characterization of normality. So this is just the usual frequency of blocks. These are non-overlapping blocks. It doesn't really matter. And the block frequency, this empirical distribution, is just, we're looking at the first n times L symbols of sequence L, and we're going to look at the frequency of each length L block W, okay? So this we call PSNL, and this is a distribution on the strings of length L, okay? So rational value probability measure on sigma L, okay? Yeah, this is probably not needed. And of course, it is based on the first NL symbols of S. Okay, so let me define now the divergence for a sequence. So yes, kind of using the divergence between the empirical distribution and the underlying distribution alpha. Okay, so I could define it for each L, I am looking at blocks of length L. I am using the empirical distribution given by these blocks on sequence S. And I am looking at the lim sup. Okay, so I am looking at longer and longer pieces of the sequence S. I'm taking the worst case. Okay, I could also do it dually with the lim, but I will not use it much today, so I will not define it. So I define it for each block length, and then what do I do in order to get a single value, okay, a single divergence? Well, the thing is that for instance, one of my goals is to characterize normality, so I'm going to make sure that all L work. So I just take the supremum. Okay? So this means that if this value is small, it's because for every block length, the empirical distribution for length L blocks is very close to alpha. And I am dividing by L because somehow, I mean, it doesn't really matter for normality, but somehow what happens when I'm looking at blocks of length L is like changing the alphabet to sigma L, changing from sigma to sigma L. So somehow the information theory fair way of getting rid of this change of alphabet is dividing by the length. Okay, so I will use this divergence for just to quantify the divergence between empirical block length distribution and alpha, and I take the supremum for all L. And I can also do it directly to compare two sequences. Okay, in two sequences I have two different empirical distributions, so I can look at also the divergence between these two. Notice that always the divergence is not symmetrical, but so in this case I am taking sides. So it's important if you have the S is going to be like the real sequence and the T is the one I'm comparing with it. And I'm taking again the lim sup. And I also, again, will take the supremum for all block length. So somehow this divergence of S/T, this is kind of showing you how different is the block distribution in S and in T. Okay? Okay. So let me just show you which is the characterization of normality I can do with this divergence. This is the usual definition of normality, except that I have an underlying distribution alpha on the alphabet. Okay. So what I say alpha S is alpha L normal when, well, the length L distribution, empirical distribution coincides with alpha. And this is a lim thing. So yes, the block frequency has to be exactly alpha. And alpha normal is normal for every L. So this is the first thing I'd like to show you today. Let's try to spend a minute reading it. This is our divergence characterization of normality. So it is equivalent. So the following conditions are equivalent. S is alpha normal in the way that's usually defined, using either overlapping or not overlapping blocks or whatever your favorite definition is. The divergence between the empirical distribution or distributions given by S and alpha is 0. Okay? Using the previous definitions. So this means, since this is 0, and divergence was defined as the supremum of the divergences for length L blocks, for each block length it has to be 0. And I can also characterize normality by comparing with other normal sequences. So for every alpha normal sequence T, the divergence of S and T has to be 0. That's also another way of looking at normality. You are normal if the empirical probability distribution that you provide is the same as for any other normal sequence. And of course, the 4 is just trivially follows from 3 because there exist alpha normal sequences. So it is the same to have that for every normal sequence, your divergence is 0, or there exist normal sequences for which the divergence is 0. So this is, as I said, an alternative characterization of normality that I think can be especially interesting when you are not in the uniform distribution. So somehow, I mean, this is also true, maybe even interesting for uniform, but if alpha is something different, you can still have this. Notice that I really need the alpha to be defined on symbols. I mean, it's not very clear to me how things would work if you had a general probability distribution that was not a product distribution. I've been thinking a bit about this. I'm not sure if exactly the divergence will work that well somehow. Because I am comparing these empirical probability distributions for different block lengths. And somehow it is quite important in this sort of comparison that I count like blocks separately, and I can nicely compose the frequencies. I'm not sure how to deal with a general distribution in which all the probabilities in different prefixes of S start behaving very differently. It can be interesting to look at. Okay, so this is the first result I wanted to show you today. And the second one is a bit of a problem because I expected Jack to have given you a crash course on gamblers. But you know about gamblers, don't you? I mean, so this is just a finite state machine. And in each state, you have a betting function. Okay, so since there are only many, finitely many states, you only have finitely many betting choices, okay? So something like that. Don't worry too much about the definition. And of course, in order to use the underlying probability distribution, I kind of modulate the payoffs. I mean, the payoffs are defined both by the betting. This is what I bet. Being in this state with this symbol, I bet this. But then I divide by alpha in order to see how much is the payoff, something like that. I wanted to show you the result, and I only have a few minutes, so let me assume that you more or less see this. This is just a usual definition of martingale based on betting. So this is the first part of our result, in which we see what happens if S is not alpha normal. If S is not alpha normal, you get at least 2 to the divergence of S with alpha times the length of W. And there's a gamma here, which is any number less than 1. So you can kind of take it off and assume it's a 1 anyway. And I even wanted to show you a bit of the proof, but I think I leave it out. But let's see. The proof is strongly based on the fact that divergence behaves very well continuously. So somehow, for instance, I get some sort of betting strategy, and I divide how much it makes in 2 parts. The first part is related to the empirical distribution versus alpha, and the second one is the empirical distribution versus what I am betting. This pi 0 shows in the proof it's related to how I define betting. So the thing is that I can try to make this go to 0 if my betting resembles very much the empirical distribution. Of course, it's not a single empirical distribution, so this is why the proof is not that's immediate. But somehow the way that this divergence behaves makes it very easy to try to even make a betting strategy that tries to resemble a whole sequence of empirical distributions. And for the other part, the way I can quantify exactly how much money I lose if I am normal is by using this idea of risk. The risk, this is a gambler G, and I am in a state Q. The risk is related to the divergence between the underlying distribution alpha and the betting I use when I am at state Q. Okay, so also the risk is related to this divergence. And of course, the risk over a finite sequence W has to be the sum of all the risks I take on the states I go through when processing W. I think I will not get into more detail today, but so the theorem is for every normal sequence, for every finite state gambler G, the payoff of G on sequence W is bounded by 2 to the minus, gamma is again any number less than 1, risk of G on W. Okay. So it's a very full, how you say, I quantify both sides of the Schnorr-Steen dichotomy. Well, there's also a result relating a finite state dimension for not normal sequence. I mean, for any sequence. I mean, so it's clear from Jack presented his result on quantifying exactly the finite state dimension for normal sequences. So this is for any sequence. And it will be very nice to have some sort of result, closer bound or even an equality for any sequence in the line of the result he presented. So we were working on it. We had something like that. But so his result was that the finite state dimension of a normal sequence is like this. Oh. Okay. No. Well, okay. Let's see. I can write it like this. Let me try. Okay. If S is beta normal. Okay. Okay. So, okay. The way, I mean, he wrote it differently, but if I am given a beta normal sequences for beta probability, a positive probability distribution on sigma, we have this, I mean, he proved this result. I mean, I wrote it slightly differently. So there is an entropy related to the underlying probability distribution, block distribution. So you have H of S over H of S plus the divergence between S and alpha. But of course, this proof requires very well behaving on the empirical distribution for S. This is why S being beta normal is good. But so I wonder if we could extend it. I mean, we have some extensions for general sequences, but at least instead of S being beta normal, I would ask you to think about only requiring that these limiting frequencies exist. So there exists for every W this limit on the number of times that block W appears over, so this this limit of pi and whatever W exists only with this. Let's see what we can prove with that, as opposed to having a very, so if I assume that S is beta normal, I am assuming that not only all these limits exist, but they also coincide exactly with beta of W, which is something that is only dependent on the symbols of W, because alpha is defined on the alphabet. But if I only assume that the limit exists, the behavior can be very different on different W's. But still, Could we get some sort of characterization of dimension like this? Thank you very much.
Maybe time for one quick question. We take the rest of the questions to the coffee room. Any immediate questions? Okay, then let's thank Elvira again.
Thank you.